Hello, this video is for Stat 310, Handout number 10, Part A, and will cover pages 1 through 10. Okay, let's go ahead and get started. So handout number 10, it will be in 3 parts. We'll be looking at Part A here, and the data set that we will be using is the Lions Males Only data set that is provided in our Google folder here. So handout number 10 considers simple linear regression. And what we have here is an article written by Whitman in 2004. And they investigate the relationship between the black pigmentation on the nose of male lions. So we can see the black on that lion's nose in regards to their age. So if a relationship can be established, then hunting guides or even hunters can use this information to avoid killing lions that are important to the sustainability of the lion pride. Data was collected on 32 different male lions from 2 different locations. The age of these lions is known, and the proportion of black pigmentation on the nose was recorded. So our response variable here is going to be the PNB, or proportion of nose black. These values are going to be between 0 and 1, 1 indicating that the nose is completely black. The independent variable, or the predictor variable, also known as the X variable, is going to be age here, and that's in years. Again, the data can be obtained in the Lions Males Only data set. Here's what that data set looks like. 32 observations. We can see that we have lions from 2 different locations. They're all male here. And then we have the predictor variable age and the response variable percent nose black, or PNB. On page 3, we have our statistical model. It's broken out into 2 pieces. We have the part that's for the mean, which is going to be this first part. So that is going to be used to express the mean of the proportion of nose black. And then the error part, or the residual part, is going to be used for the variability in our model. So much like the models that we were considering in handout number 8 and handout number 9. The difference being here is that the predictor variable, or the factor variable, is actually quantitative in nature. It's actually a number. So in our model, so let's look at these 2 pieces. We have the expectation part, or the mean part, which we express as just E sub y given by beta 0 plus beta 1 times x. And all this is saying is that the mean of the response variable can be determined using a linear function of x. The variability here, so the variability in the response, comes from the variability in the error term, or the residuals. And we just set that to some constant value. So the variance of the response is assumed to follow a normal distribution, is constant, and does not depend on a does not depend on the predictor variable or the independent variables. So this is just our constant variance assumption, like we had in handout 8 and 9 as well. If we put this in the context of this problem, we are trying to model the PNB, which again is the proportion nose black, as a function of age. So the goal here is to understand the true or the exact relationship that exists between age and PNB. So what is the relationship for all the lions? That is the goal, is to try to understand that situation. Unfortunately, we can't understand that situation because it's not going to be feasible to get these recordings on all lions. So instead, what we get is a glimpse of this relationship through the data that we have. So here's a scatter plot of the data, has the trend line in it, has the equation of the trend line, and this is coming from the data that we have. But what we'd really like to understand is the true relationship, which is not known to us. It's probably going to be slightly different than what I'm seeing in this plot. That true relationship, though, is given by this linear function. So if we go over here to the right and look, it's given by the expectation for the proportion of nose black is given by beta 0 plus beta 1 times age, which is just a line equation for a line. The beta 0 in this line just represents the y-intercept, and the slope of this line represents just the rise over run. So here, in the context of this problem, the slope is going to indicate how much do I expect the PNB, or proportion nose black, to go up for every additional run. So if I run 1, or if I increase age by 1 year, how much can I expect the PNB value to go up? That's what the slope is going to represent here. Again, our goal is to understand this true relationship, but what we get is a glimpse through the data that we have collected. So our analysis here of simple linear regression has to deal with how do I use this information that I get from the data that I've collected to infer or make decisions about what the true relationship looks like. Okay, so how do I fit this model inside of JUMP? I do this model fit just like we did before. Okay, so I'm going to put my response variable here in the Y box, and I'm going to put my construct model effects, or age, down here in my construct model effects box. So let's go over and JUMP and do that. So I'm going to select Analyze Fit Model. Proportion nose black is going to go in my response box. And then age is going to go down here in the construct model effects box. Age here is a numeric quantity. We can see that that's a numeric quantity. In handouts number 8 and 9, those were different groups or settings or factors. But this is the first time where my predictor variable is a numeric quantity and my response is a numeric quantity. So this is a setup for simple linear regression, when both the predictor and the response are quantitative in nature. Okay, so let's go ahead and hit run here. And we're going to get a set of output here. The first is going to be just my scatter plot, which I've already included in the notes there. We have a set of output down here towards the bottom. Let me bring that up a little bit so we can see that. And that output is the summary of fit, the analysis of variance, and the parameter estimates. These are all important to our understanding of the simple linear regression model. So that's what we'll talk about next, are each of these components. So I've broken these out into 3 different components. We'll first talk about the analysis of variance part. So understanding the output, part 1 here. These terms, we have seen these earlier in the semester, the sums of squares total, the sums of squares error, and the sums of squares model. Now the structure of my model is slightly different than what we've had previously. Again, because both the x and the y are quantitative in nature. But these ideas still hold. The sums of squares total would be the total amount of residual from the mean. So the average here looks like about 0.35. This is the average PNB. So if I took all the lines and just did an average, I would get 0.35 or so. I can compute the residuals from that average. I would square those and add all those up, and that would be sums of squares C total, or corrected total. What the corrected stands for there is just that I'm using the average of all of the data there. The degrees of freedom associated with that quantity is going to be just the number of observations minus 1. The reason it's minus 1 is because I'm only estimating one thing here, the average. Now let's talk about the error term. The error term is going to be the residuals squared, but here using the model. Okay, so the model is going to be that trend line we talked about up above. the residuals here are definitely going to be smaller, because we can see that these residuals up on the upper end now are much smaller than if I were to use the average. Okay, so overall I'm going to have a lot less error by using my model. If I take all of these residuals here on the right, square them, and add them all up, I'm going to get 0.438. The degrees of freedom for this calculation is going to be n minus the number of parameters in my model. Now my model had a beta 0 and a beta 1 in it, so it's going to be 32 minus 2, or 30 degrees of freedom. So again, if we go back up and look at the form of our model, it has a beta 0 that has to be estimated, and it has a beta 1 that has to be estimated. So there's two terms here that are being estimated to compute the mean. The sums of squares for the model, then, are just the difference between these two. And also the degrees of freedom for the model would be the difference between the degrees of freedom. We take these sums of squares and divide by their degrees of freedom. That's how we get the mean squares. So 0.438 divided by 30 here is going to give me a mean square of 0.015. If I take the ratio of these two quantities, of these two mean squares, I get my F ratio. So there's not much error left. Okay, there's not much sums of square error left after fitting this model. So that makes this F ratio very large, which in turn makes my p-value very, very small. So what is this actually testing here? The H0 for the overall test is just asking whether or not a linear relationship exists between these two variables. The p-value here is less than 0.05, so we get to say that we are 95% certain that a relationship exists between P and B and age. Probably should add my p-value quantity there for completeness. So there is indeed a relationship that exists between proportion of nose black and age. Okay, that's the overall test. How about part 2 of the output? Part 2 of the output is the summary of fit part. The R squared is an important quantity that we use for determining how well our model is doing. What the R squared is simply the proportion of variability in the model. Okay, so the model part here is just identifying how much of the sums of squares is being taken up by the model. In this particular case, that is 0.87. How much sums of squares did I start with? 1.308. That ratio there, 0.87 divided by 1.308, is my R squared. So again, the sums of squares model is how much of the error, or how much of the total sums of squares, can be attributed to age. And that's 0.87 out of the total of 1.309. So that R squared is about 67% or so. So our interpretation of that quantity is 67% of the variation in proportion of nose black. That's my response here. So 67% of the variation in the proportion of nose black can be explained using this model with age. So age is certainly has an impact on proportion of nose black. Another way to think of this, of all the things that influences the lion's nose to be black, about 2/3 of it is due to age. So that's a pretty good model. We will not worry about R squared adjusted. Let's move on to root mean square error. root mean square error here is 0.121. And what this quantity represents, again, is just the average residual, or the average error. So this gives me an indication about the average amount of error that I can expect in trying to make predictions for the proportion of nose black. This is about 0.12, or about 12%. So when I make predictions, the error in my predictions, on average, will be about 12% off. The mean of the response is just simply the average of all the proportion nose black values, which was 0.35 in this case. Again, that quantity is used when I'm trying to compute the sums of squares total. Observations here is just the number of observations, which would be 32. Okay, let's go to part 3, the parameter estimate part. We have 4 columns here. We have the estimate column, which are just used to obtain, that's the equation of my line. So the intercept is 0.072, and the age is 0.064. The slope, excuse me, is 0.064. So this quantity here, the 0.072, is the beta 0 hat, and this quantity here is the beta 1 hat. Again, the hats just indicate that they're coming from the data. We even would put a hat on the expectation. So the expected proportion of nose black would be given by this equation here. These are the standard errors for these quantities. So these would be used when constructing a confidence interval. Here are the t ratios and probabilities, or p-values, for the following tests. So the intercept, what we are testing with the intercept is just whether or not the y-intercept is equal to 0. The p-value for that is 0.0953. So what the intercept would indicate is what can I expect the proportion of nose black to be when the age is at 0. Okay, so that would be a newborn lion, I guess. So when a lion is just born, what can I expect their proportion of nose black to be? Well, the estimate from the data is about 7%. Can I say that that's going to be different than 0? No, we can't. Not quite. So it's possible, or it's reasonable, to assume that the proportion of nose that will be black when a lion is born could be 0. So there might not be any black on their nose when they're born. So we do not, the correct conclusion or full conclusion here, we do not have enough evidence to say that the true y-intercept will differ from 0. Again, that's the tests that are given underneath the parameter estimates. Okay, how about the one for the slope, or the age row here? Well, that is testing whether or not the slope is equal to 0. So is the slope equal to 0 or not? And the p-value here, which is a typo, is less than 0.0001. Okay, so we're getting that from this quantity right here. So we do, copy and paste mistakes there, we do have enough evidence to say that the true slope is different than 0. In particular, we can say that there is indeed a linear relationship between the proportion nose black and age. Now it turns out that this test right here, for simple linear regression anyway, this test right here is the same as the overall test up above. If the slope is flat, well, that situation is this here on the left. This would be a flat slope. And this is what was used to obtain the overall test up above. We use this sums of squares from this model, 1.308, in our analysis of variance table here to obtain this F ratio and this probability. The conclusion from the overall test was that we said that a relationship exists between these two quantities. Well, that's equivalent to asking whether or not the slope is flat. Up here, we decided that there was indeed a relationship from the overall test. Well, that implies that the slope is not going to be flat, that there's indeed something going on between the age and proportion nose black. So this test here is actually just a reiteration or the same test as the overall test. Now that's only true when you have just simple linear regression, when there's only one x variable in your model. We can obtain 95% confidence intervals for beta 0 and beta 1 through the following. So the confidence intervals are not given to me automatically. I need to go under Regression Reports and select Show All Confidence Intervals. So if I do that here, Regression Reports, this is from the red drop-down menu, and say Show All Confidence Intervals. And that's going to produce confidence intervals for the beta 0 and beta 1. And that's what we have here on page 9. So if we look at the confidence interval maybe for the slope, this is going from about 5% up to about 8%. Okay, so we are 95% certain that the expected increase in the proportionate black nose is going to go up by about 5% to 8% for a 1-year increase in the lion's age. Okay, so for this is the slope, so this is all just for a 1-year increase in the lion's age. So practically speaking, this is going up. If I even round that a little bit more, I can say that proportion of nose black goes up by 5 to 8% per year. Page 10 includes the formulas that are used to obtain those confidence intervals. I'm not going to ask you to use those formulas, but they are here for completeness on page 10. Okay, that does it then for handout number 10, Part A, pages 1 through 10. Thank you. Have a good night.